So any questions about last lecture or lab 1? Seems like lab 1 went pretty well. One thing I noticed last week, though, I never noticed this before, but I was helping out a student and we were doing a test case of 0. Any of you try that? So one of the strange things that happens there, assuming you set it up the way I did, so if you set up your initial guess to be 256 and your initial step to be 128, if you put in an input of 0, a weird thing happens. If you look at what the value of 2 raised to the negative 14th power is 6 times 10 to the negative 5th power, so it's 6 100,000ths, right? Well, the problem is that's basically the smallest number you can represent. The problem is that if you put 0 in and you have guess squared, at some point the guess squared gets to be lower than 6 times 10 to the negative 5th power down here before it finishes the algorithm. And as a result, sometimes when you put 0 in, you'll get a non-zero answer because your algorithm gets fooled into thinking that it actually hit 0 for guess squared as soon as it has a guess squared that is less than 2 to the negative 14th power, which is less than the precision of the format. Okay, so and now one way to fix that is to don't convert the guess squared to 3214. Leave it in 6428. And then compare it to the input value as a 6428 number. You know, that's one way to fix that. The other problem, though, is even if you do that, what ends up happening is that you'll decrement every time through the algorithm. You always subtract the guess, but by the end of the algorithm, you have 1 left in the guess and 0 in your step. So the smallest number that you can have as an answer there would be 1, or 1 times 2 to the negative 14th power. So the way to fix that is I think you can start your guess off at 0 and use 256 as your step. But anyway, I'm not splitting hairs with that. I'm not going to worry if your input value of 0 doesn't give a 0 output, as long as it's a small number. I'm fine with that. Okay. But I didn't realize that until just last week, end of last week. Okay, so last week we assigned lab project 2, and by this point in the course you have about half of the information you need to fully execute that lab. But we were hoping that you could just kind of get up running with some of the tools in the lab. So the lab sheet has some steps to get started. It says to add a script to your bash RC file, to download the project skeleton and extract it. Hopefully you're all comfortable with doing that from 2.15. It's basic Linux stuff. I don't remember what format. I think it's a tar GZ file, or it might be a bzip7 or whatever the case may be. But it's an archive file. You extract it. Then you run. Now we have a script here called CSCE 611. And that script is inside the project skeleton directory, as well as the sort of the skeleton or the template for your project. That script allows you to compile and to program the board without ever going into Quartus, which is kind of neat, but you should also be familiar with Quartus too. It's not really hard to use. So I'm going to show you Quartus today, and then you guys will have the option of using Quartus or using this script and just doing everything at the command line. That'll be up to you. And then the objective, of course, is to instance 8 7-segment decoders, which will allow you to flip the switches and have each group of 4 consecutive switches be an input into each of the 7-segment decoders. The problem, of course, is that there's only 18 of these switches, so that only gives you room for 6.5 digits, right? And so what will happen is that the leftmost 2 digits will always be 0, right? And you might say, well, then that kind of stinks, and why do we need 8 decoders? That's a waste. Well, because in the next lab you'll be using all 8 decoders because we won't be feeding them with the switches. Okay. Okay, so in today's lecture, I'm going to I'm going to finish talking about everything you need to know about combinational logic design in SystemVerilog, and you'll have almost everything you need to finish the lab. The only piece you'll be missing by the end of this lecture is this part, a self-checking test bench. Self-checking test bench is a SystemVerilog file that tests another SystemVerilog file, but it requires sequential logic. It requires you to have an always statement, which is sequential logic. I won't get to that till the next lecture. But today I'll finish all the combinational stuff, which, like I said, will comprise almost all of this lab. Okay. So just to quickly review what we talked about last time, I went through this stuff pretty fast. In this course, SystemVerilog is a way to describe the behavior. We compile it into a structure, which is called a netlist, or a schematic, which is basically primitive blocks that are interconnected, and then those get mapped onto the FPGA when you program the FPGA. We talked about this idea of hierarchy and regularity quite a bit. And that was mostly, and Charles used to always say, man, that's just too abstract, that no one's paying attention to that. But the reason I go over that and I emphasize that is because that's the reason why you have modules in Verilog. Because when you write code in Verilog, it's module, 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 module. And it's like, why so much modules? Why is there one module per file? What's all this? It's all because of these concepts. This is the way that you develop complex digital designs. I mentioned that we're doing both combinational and sequential logic. I guess that you didn't cover sequential logic much in 212, so that'll be new for most of you. Combinational logic is everything you focused on in 212, which is basically digital logic gates where the output is just a function of the input, right? And so you change an input and the output automatically updates. In SystemVerilog, you can implement combinational logic as single lines of code, and then those lines of code represent circuits, so there's no ordering. It uses concurrent semantics, meaning that if any of the inputs change, the output changes, regardless of the ordering of lines. So you can scramble your lines of code, and it won't make any difference. Okay, then we talked about logic circuits, and we talked about four-state logic, where you can have a wire can have a 0 or 1, or an X or a Z, and I talked about what X and Z stands for. And then I gave you a little bit of history of HDL, and then we talked about simulation versus synthesis. And then we talked about behavioral versus structural code. So behavioral code is when you're basically designing something that can be built as a circuit. It has to be converted to a circuit, whereas structural code is where you're defining a schematic, essentially. So when the compiler compiles your structural code, it doesn't have a very hard job. Just puts the module there and connects it with wires, basically, right? It goes almost straight from your code to the netlist, the structural code. And then, of course, at some point it flattens the hierarchy out and you end up with a big, massive, unreadable list of wires, right? But behavioral code is when you actually have code, like programming code in the traditional sense. Okay, so we looked at some syntax. We looked at the module line, the assign statement, or sometimes it's called the concurrent assignment statement or the continuous assignment statement. So this is for making this assign statement is for whenever you need some real simple logic you want to stick in. It's good for multiplexers and adders and simple logic. We talked about syntax. Okay, and then we got to this part, which is the part that tends to confuse students. This is the idea that when you instance modules and you connect them with wires, you end up with the same physical wire, but it's called different things depending on where you're looking at it in the hierarchy. It's almost like a scope, like in programming languages. So the idea is that you've got A, B, and C inside of this AND gate that map directly into the A, B, and C inside the AND gate that's inside the NAND gate, but then there's this Y output that's called Y inside of this module, but once you come out to the larger module, it's now called N1 because of that connection is made right here when you instance that guy. So the problem here is that when you're simulating, it's easy to get confused because if you change N1, or if Y changes in here, it'll automatically, this N1 will be will always be equal to Y. N1 in the NAND gate will always be equal to the Y in the AND gate, right? And sometimes those connections go very far down into the hierarchy. Okay, so that part is, if you're comfortable with that, then you shouldn't have too much trouble with the language. Okay, then we talked about simulation and bitwise operators and multi-bit signals or wires or logics or whatever you call them. Most of these objects in here that can take values represent wires, right? Now that isn't always the case once we get into the assign statement. The always statement, which is also known as a process, which allows you to create more abstract behaviors. But in all the examples I've shown you so far, whenever I have something declared as logic, it's a wire. It will be a wire somewhere in your final design you put on the FPGA. And of course, wires can be multiple. Well, can be instances multiple bits, like multiple parallel wires. Okay, and then we talked about the ternary statement, which is used for muxes. And then I think that's where we left off last time. So here's another example. These come from the textbook. This is creating a full adder. And I'm going to go through an example of this. I'm going to demo this live. But they implemented theirs a little differently than I'm going to do mine. They have these two internal signals called P and G that stand for propagate and generate. These are building blocks for carry look ahead adders. And then they assign those, and then they use these in the assign statements down here. Now you might say, well, wait a minute, hold on now. You're assigning something in one line of code, and then you're using that as an input on a subsequent line of code, right? Because I assign P here, and then I use P down here. So P is an output, it's on the left-hand side of the equal sign, and here it's an input, right? Because it's on the right-hand side of the equal sign. So how does that work if there's no order to these lines of code? Well, what ends up happening is when you implement this, you have a circuit generating P and a circuit that's consuming P and generating S. So what ends up happening is you get a chain reaction effect, whereas if A or B changes, if the state of A or B changes, in other words, if they go from low to high or high to low, or if they go from high to Z or whatever, their value changes, it's going to activate this line of code, which will update P, which will then, as a consequence of that, will update this assign statement, right? So you end up with these chains of events. And so when you simulate this, the software you're simulating it with is called a discrete event simulator, because it works by monitoring the state and updating and responding to events. The problem is that if you have a circular chain of events where one event triggers another one and that one triggers the original one, now you're in trouble because the software hangs and there's nothing you can do about that, aside from randomly deleting code to try to use trial and error to track down where that cycle is. So you got to be careful that you don't have a combinatorial loop inside your circuit, because the simulator has no way of detecting that, because it'll just endlessly trigger things and it gets hung up, right? The idea is that anytime something changes, you can have chain reactions of events, but at some point the circuit will stabilize and just remain static, at which point the simulator returns control to you as a user, right? But if that never happens, you end up hung. Yes?
Does that mean you can't make a D-latch?
You can, but that's a special case where a D-latch will stabilize. So it still has those circular feedback connections, but it'll eventually stabilize. But if you have an oscillator, yeah, then you're finished. You try to run that in Model Sim, and it'll just hang. So it's easy. Now you might say, well, how likely is this going to happen for our designs? The only time in this class where this comes up is when we implement branch instructions in the CPU. There's a potential there for that kind of loop, because when the CPU fetches a branch, it has to stall. It has to generate a stall. In fact, it has to stall the subsequent instruction that's come into the CPU. Every CPU has this problem. Branch instructions are fundamentally expensive because by the time you know it's even a branch instruction, and by the time you've resolved the branch instruction, you've already grabbed the subsequent instructions, right? It's too late to do anything. You got to flush them out, stall them, right? So in our CPU, we're going to fetch a branch and then issue a stall signal, which will tell the control unit, hey, stall, don't do anything, like ignore the next instruction. We fetched it, but we weren't supposed to because we're supposed to take a branch. If you don't put a flip-flop in that feedback loop, what ends up happening is the controller says, I got a branch, stall. And then that stall, if that stall comes back combinationally, the controller says, oh, what am I doing stalling? It's a stall. I don't need to stall. It's a bubble. I don't need to stall. It's a no-op. So it unstalls, which then brings the branch back, and then it stalls. And then it sees the stall, and it says, I don't need to stall, and then it unstalls. And it does that endlessly. The way to stop that is you put a flip-flop in that path. So you basically say, I want to stall, but I don't want to stall now. I want to stall in the next cycle. One cycle in the future I'm going to stall. I'm not going to stall in the current cycle, right? But a lot of students in this class will forget to put that flip-flop in there, and it causes that combinatorial loop. Okay, and then the operators in SystemVerilog are basically identical to Java, Python, C++. The only difference is you actually have an XNOR and a NAND operator, tilde ampersand, which is kind of weird. And it has this arithmetic shift, which is actually, the shift operator is, you have that in every language. But the arithmetic shift, which is where you have the 3 less than or 3 greater than, is for arithmetic shifts when you want to shift the sign bit from the left, right? Shift in the sign bit. Now you might say, wait a minute, hold on, if I'm shifting left, then the sign bit isn't going to get shifted. Yeah, but you might be shifting left by a negative shift amount, in which case it's effectively a right shift, in which case you have to worry about the sign bit. So you've got those. Now you might say, wait a minute, why doesn't Java have that? Well, because Java doesn't need that, because Java knows whether you're doing an arithmetic or a logical shift based on whether you declared the value you're shifting as an unsigned or assigned integer, right? But remember, in Verilog we don't have that, we just have logic, right? There's no sign. There kind of is signed or unsigned, but it's kind of strange. We'll talk about that when we get to the ALU a little bit more. But generally speaking, Verilog doesn't really know signed or unsigned. You declare everything as a logic, and which is why you need to have these 2 separate types of shifts. Okay. Okay, and I think the last, there's 2 more things I want to talk about, and then I'll show you an example. The other thing is whenever you have a constant in your code, like just a number, right? Like, for example, when you increment a loop, you add 1, right? Or you compare something against a number. You have to specify how many bits that number is. Because, like, for example, in traditional programming languages, they can kind of infer what it is. I mean, because most things are, the word size, 32 bits or 64 bits, right, depending on the word size. But in Java, in Verilog, you want to be able to specify your bit width for a constant. Additionally, you may want to specify the number as decimal or binary or hexadecimal or octal, right? So they have a special way to do that in Verilog. So for example, you put the number of bits and then an apostrophe. Regular apostrophe. So if you copy some data in from a Word document or a PowerPoint or a PDF and there's a smart apostrophe, that'll break model. It doesn't know how to deal with that. It's a regular apostrophe. So 3 apostrophe means 3 bits. And then you give it a base, which could be B for binary, H for hex, O for octal, or D for decimal, and then the number. So for instance, if you put 8 apostrophe B11, that's the binary value of 11 or the decimal value of 3, and it's going to be put into 8 bits. And they might say, well, wait a minute, hold on. I don't need 8 bits to store 3. I only need 2 bits. Well, yeah, it's gonna put zeros. It's gonna pad it with zeros when you do that. Okay, so you'll have 6 zeros and then 1 1. Okay. Now you can get away with not using this because the default base is decimal, which is kind of surprising actually, since this is a hardware language. You would think it would be hex or binary, but the default base is base 10. And the default width is 32 bits. So if you put 42, well, it says unsigned. I think it actually, depending on what you're compiling with, I think the default width is 32. But you should avoid doing that. You should be, one of the things you'll notice in this class is that when you write this code, you have to be a little bit more careful than you are when you write software, because any minor issue can break your whole design. So you should be precise and specify the bit width when you put these numbers in. And then finally, bit manipulations. So there's a couple ways that you can slice bits out of a wider logic signal, right? Or you can concatenate bits, or you can rearrange bits, or you can duplicate bits. How do you do that? Well, if you use the brackets, you can create a bit slice. So for example, A bracket 2:1 means I want bits 2 down to 1 of signal A. Okay, so that's a way to kind of take out 2 of the bits and just rip them out, right? You can also say, A2, which is just bit 2. You can also concatenate bits using the curly brace. So if you use curly braces and then you list signals, some of which can be sliced, separated by commas, it'll just concatenate. It'll concatenate them together to a wider signal. And then finally, you can duplicate. I don't have that here. Well, hold on, let me show you this example. So if you type assign, let's see, assign y is curly brace A 2 down to 1, comma, and then notice I have, this is the duplication operator. Curly brace 3, curly brace B of 0, curly brace. That's the duplication operator. That will take bit 0 of signal B and duplicate it 3 times. And you have, now when you do that, you have to use both inner and outer curly braces. You might think, he probably just put the outer ones there. No, you have to. You have to do it exactly that way. You have to say outer curly brace, duplication factor, inner curly brace, signal you're duplicating. Make sense? Okay, so in that case, this is effectively creating a signal that's going to be A bit 2 as the most significant bit, because it's the bits are ordered from left to right, most significant to least significant. So this is creating a signal that's A bit 2, A bit 1, A bit 0. Oh, sorry, no, not A bit 0. We left that one out. B bit 0, B bit 0, B bit 0, because we've duplicated B bit 0, and then A bit 0, and then a constant of 100010. Now notice I put an underscore in that constant. The underscores are for readability purposes. They're actually ignored by the compiler, so it's common to see underscores in numbers, especially binary numbers, because they're used to separate fields, bit fields. So it's for readability. So like for example, when we create a test bench, you'll have test vectors that'll have all the inputs and the expected output, but they're all together, hard to read. So put the underscores in there and it kind of breaks it up into segments, right? Takes a big number and kind of breaks it up. Okay, so that's it. That's bit manipulation. Here's another example. This is pretty common. Sign extending. Hopefully you guys talked about this in 212. Or like, for example, the RISC-V processor allows you to have a 12-bit immediate value, right? And you can add that immediate value to a register, right? The problem is that the register is 32 bits and the immediate value is 12 bits. So how do you add a 32-bit number to a 12-bit number? Well, you have to sign extend the 12-bit number. So you basically take whatever its sign bit was, or is, that's bit 11, right? Because the 12-bit number is 11 down to 0. And you take that bit and you replicate it 20 times, right? That gives you the other 20 bits. In this case, I've got a 16-bit number that I've sign extended with 16 sign bits. So I took bit 15, which is the sign bit of the 16-bit number, and I kind of just filled up the empty bit slots with the sign bit on the left. Okay. Alrighty. Okay. Here's another example of this kind of combines a lot of stuff together. This is a 2-input 8-bit mux. And we're building it with structural Verilog by combining together two 2-input 4-bit muxes, right? So the idea is that you have a 4-bit mux and a 4-bit mux. So you take the upper 4 bits of the inputs and you stick them in this mux, and the lower 4 bits, you put them into that mux, and then the output needs to be combined. You know, the outputs of those two smaller muxes are combined into 8 bits, and then the select input is fanned out to both. The select controls both in parallel, but the inputs are split, 4 and 4, right? So you can see that this combines together structural Verilog, bit slicing, and multi-bit signals, as well as the, well, I was going to say the ternary operator, but that's not in here because this is purely structural. The ternary operator, which actually implements the actual mux behavior, it would be inside of this, you'd have to drill down to get to that, into the hierarchy. We don't see that in here. We don't see the behavior, we just see the structure. And that's common in Verilog. Most Verilog is structural. The only behavioral code is usually at the most primitive nodes, the leaf nodes. Okay? Oh, one other thing I want to mention too, I skipped over it before. This part, this assign statement is assigning a value y, and then on the left-hand side of the assignment statement, they're using a concatenation, which is kind of wild. So you're taking a signal and you're splitting that signal across 3 bits, and then assigning it to specific bits within A and B, right? You guys all see that? So I'm using the bit slicing and the concatenation on the assignment side, on the output side, which is valid in Verilog. You can do that. Okay, and then yeah, one last topic before I get to simulation is reduction operators. These are kind of neat, but I very rarely use these. But a reduction operator is when you have a multi-bit signal, like you have an 8-bit signal, and you want to just take all 8 of the bits and just kind of AND them all together and have one output, right? So you want to just create an 8-input AND gate, essentially. Or you could do it with NAND, OR, NOR, XOR, or XNOR, right? Also known as XOR. So a reduction operator is where you basically just have a signal name and then you just stick a little ampersand in front of it, for instance, and that'll create a big AND gate that feeds all the inputs, all the individual bits of A into an AND gate. Like I said, those are not super common. One last thing I want to mention here, you might have noticed already that I've been a little inconsistent with one element of the syntax here, and this is because this came from the book. Notice where it says input 790A, it doesn't say input logic, it just says input, right? Okay, well, that is something that you can almost always get away with. And it works fine for inputs. But if you have an output, and if you drive that output with an always statement, which I'll cover in the next lecture, which is essentially any kind of sequential logic or any complex abstract behavioral code, then you have to have the logic. I have to output logic, right? So my style now is to just always put logic, input logic, output logic on everything. But you'll notice, like on these slides, sometimes they'll leave it out. And even in Charles's code that he wrote for the template that we provide you in the lab skeleton for the top level design, I think he left out logic. But if you ever get it, if you do that, and if you get an error message about driving a structural net expression or something, it's probably because you have to put the logic back in. Does that make sense? That's one of the weird things about SystemVerilog that they didn't fix. I don't like that. I wish they would have just been consistent. But I tend to always declare those inputs and outputs with logic. Okay, so let me show you an example. I have a virtual machine here, and let's do an example just to give you an idea of what the process that you follow when you do this stuff. So I'm going to create a directory called adder, and just to hold my stuff, and then I'm going to create a file here. Oh, hold on, let me do this. Yeah. Okay. I like to use tmux so I can edit in one side and run it on the other side. So I'm going to create a file here called full adder. I'm going to create a full adder.sv, and so in here I'll have a module line called full adder, and then I need to have my input. Now, like I said, I'm going to use input logic. So if you remember from 211, a full adder is a single bit adder. It takes two inputs, A and B, which are single bit inputs, and then it takes a third input called carry in, right, which is the carry out from the previous bit, right? So basically you have three single bit inputs, which can give you, and you add them together, and that'll give you a numeric sum from 0 to 3, right? You can have all zeros, in which case the sum is 0, or you can have all ones, in which case the sum is 3. So there has to be two bits of output, and the outputs are usually called S for sum and carry out, right? And then you have your semicolon and end module. And no semicolon after end module, unclear why that's the case. Okay, okay, so try to format this a little better. Okay, so this will just have an assign where I'm going to assign S to be, well, how does a full adder work? S is going to be basically taking the three inputs and XORing them together because I want to calculate the modulo 2, right? So in other words, I want to calculate, S is the least significant bit of the output. So if the sum of the inputs is an odd number, that should be 1. If it's an even number, it should be 0. And I can implement that with a XOR. So I'll say A, XOR B, XOR C, C in, and then I'll also assign C out to be, now C out is the carry out. This one's a little bit more complicated. This has to be set whenever the sum is 2 or 3. Right? So that would only happen if basically at least two of the inputs were set, right? So I have to say A and B, or A and C in, or B and C, right? So as long as two of them are set, my carry out is 1. If all three are set, well, that's fine. My carry out's still 1, right? C in, sorry. Yes, thank you. C in. Okay, any questions about that? All right, so that's a simple full adder, and so what do I do now? How do I test this? So we're using a, like I mentioned, a program called, I'll call it Model Sim, but it's actually called Quest2Sim. It's the improved version of Model Sim, so the marketing people are always trying to come up with more exciting names. So the first thing you have to do is you have to compile this code into a binary format that is usable for the discrete event simulator when you run the simulation engine. So to do that, you just type vlog and then the file name, fulladder.v. Now, if you get any syntax errors, they'll be shown there. Okay. You can also say vlog star.sv if you have a group of SystemVerilog files you want to compile. The problem with that, though, is that if you do that, be aware that it's going to scroll, and so you might have an error in a file that'll scroll by, and then you'll see 0 errors at the bottom. You're like, I guess I don't have 0 errors, but what you didn't realize is that one of the earlier files that was compiled had errors. So make sure, if you do a batch compile, make sure you scroll up and check for any errors in any of the files. Now, once you have that compiled, what you get here is it creates a work directory in whatever directory it is you did that compile. The work directory is the work is the name of the library that they got compiled into, which is pretty much a meaningless concept. But it's just a library is just a container for all of the modules that you as a user have compiled. Okay, so if you want to actually start Model Sim, you just type vsim, and then I'll just type vsim full adder. There is a way to pick what you want to simulate after Model Sim starts, but I like to just say vsim and then just space and then the design I want to simulate. So once you do that, you get this GUI. Now you'll notice that it's a little, it's a little tough to read. I'm always trying to scale this to. Yes, even if I scale it up, for some reason the fonts say small, so it's a little tough to see. But what you're seeing here is this is the simulation window. It shows the full adder. I can also switch to my library tab, and you can see there's my work library with the full adder in it. You can see there's other libraries that are loaded by default, but obviously I just care about the full adder and the work library. So over here in Sim, I've got the full adder. I don't know what this standard thing is. I don't know what that is, but anyway, I only care about the full adder. And when I click on the full adder over here in the objects window, I can see my signals A, B, C, and S and C out. And then I can I can just select all of those guys and say add to wave, and it adds this to a waveform. This is the wave that I've been showing, throughout the lectures here. And then you can see these guys in the waveform, and there's a little button down here where you can turn off the prefixes. The prefixes show where that signal is in the hierarchy. Sometimes you want it on, but a lot of times it's so long that you don't want to see it. So you can turn it off. And then basically there's nothing here. Now I can run the simulation by clicking this run button. You can also type run down here if you want in the command window. Or you can hit run. And you'll notice that A, B, and CN are blue lines, which is Z. That's a high impedance. And S and C out are X, which are the X is conflict or don't care or unknown. If this were VHDL, it wouldn't be X, it would be U, which unknown, which I think is better. But for some reason, Verilog uses X for unknown values. But generally speaking, red means something's wrong, right? Blue is, floating, not great, but red means there's a problem. So what do I do here? The problem is I don't have anyone driving the inputs. I don't have a stimulus. So to get the stimulus going, normally you have a test bench for that. But I haven't covered that yet, so I'm going to show you another way to do it in ModelSim. You can just do a right click here and you can say force. Actually, force allows you to set it to a value. But instead of doing that, I'm going to say, let me show you how to do that in the command line first. Let me go to the command line. So you can use the GUI or the command line for this stuff. In the command line, I can type, I could type force A to be 1, force B to be 0, and force C in to be 1. And then I do that, nothing changes because I have to advance the simulation, right? Because what happened was those forces are taking effect at the current simulation time, which is 500 nanoseconds, right? So after I make those changes, I have to then advance the simulation to see the impact of that. And you can see that A transitioned from Z to high, B transitioned from Z to low, CN transitioned from Z to high, and then S transitioned from unknown X down to 0 because the sum is 2. So sum is 0. And C out, carry out, is 1, right? Now the other thing you could do is, of course this is static, it doesn't change now, right? So that's kind of boring. But if I go over here and I right click clock, I can set A up to be a clock with a period of 100. I'm just going to let that default go. And then I'm going to right click B and say clock, and I'll say 200 for its period. So it's a double, I'm going to have a double period versus A. And then CN, I'll have a double period versus B, which is going to be 400. And so this will give me, this will turn each of those into a clock, but each clock will have double the period of the least significant clock. So I'll get a counting sequence. At least I should, if I did this right. Yeah, there we go. Yeah, there we go. So this should be counting from 0 to 7 back to 0. So does it? Let's see, 1. Well, there's 1, 1. A is the least significant, so that's 3. That's 2. That's, it's counting down. Oh, that's weird. 0, 3. Okay, well, it's working, but it's counting down. It goes from 0 here. And by the way, I'm dragging the cursor, and I'm looking at the values over here. These values show me, the values here represent the value at that point, at that instant in time where the cursor intersects the horizontal axis. So if you put your cursor at a moment in time, that's what those values were at that moment in time. So yeah, so it's counting down. 7, 6, 5, 4, 3, 2, 1, and then 0. And then I can also look at each one of the corresponding outputs, and in my mind I can say, well, is that what I expect? I mean, if there's 3 inputs, should S and carry out both be 0? Well, yeah, they should be. Now this is, by the way, if I were to fully test this, I'd have to look at S and C out for all 8 combinations of inputs, which is tedious. This is the reason why you would want to design a test bench. But if you don't want to take the time to design a test bench because you might be like, this is a simple thing, I can just use force commands, then that would be the way that you test it. Okay, so I've got that simulated now. Now let's go in and make something a little bigger here using this thing. So if I go back to my terminal, okay, so vsplit, yeah. Okay, so let me edit a new thing here called add8.sv. Okay, so now I'm going to create another module called add8. And the input here is going to be input logic. I'm going to have a 7-bit input called A. And a, hold on, I'll use shorthand here. A comma B, they're both 7 inputs. And then an output logic. I guess I'll go 7 bits for the output too. Sum. And then end module. And I don't know why the indenter is not working, right? Huh, okay. And so for this, I'm gonna just use some structural Verilog. So I'll say full adder, add 0, that'll be bit 0. And then I'm going to connect its A to A bit 0. And then I'm going to connect its B to B bit 0. And then I'm going to connect its carry in to something, I don't know yet. Then I'm going to connect its S to some bit 0. And then I'm going to connect its carry out to something. Okay, so now I've taken a full adder, I've created an 8-bit adder, I dropped in a full adder, and I connected some of the signals. The question is, what do I use for the carry chain? Well, for that, I'm going to need an internal signal. So I'm going to say logic 7 down to 0 carries. Not carries. Now this will be this internal thing is going to be used for inputs and outputs among these adders, these full adders, right? So the first full adder, I'm actually going to put a hard-coded 0. No, 0, 1 bit. 1 apostrophe B 0. So I'm going to assume that the first carry in is 0, but then the second carry in is, or the carry out of that will be carries of bit 0. Does that make sense? Right? So I'm not going to have a carry in. And then I'm going to take this guy and copy him. 2, 3, 4, 5, 6, 7. That was probably a mistake. But okay, so then I'm going to go ahead and I'm going to just enumerate the names of these guys. Add 1, 2, 3, 4, 5, 6, 7, and then each one of them is going to get its own pair of inputs for A and B. So 1, 2, 3, 4, 5, 6, 7, and then that takes care of A, and B is going to be 0, 1, 2, 3, 4, 5, 6, 7, and then sum, I'll do the same thing. Now you might imagine there is a shortcut for doing this. It's called a generate statement, but I'm just going to show you the long version for now. B, sum 6, sum 7. Okay, now for the carries, the first guy is going to carry out 0. Next one's going to carry out 1, 2, 3, 4, 5, 6, 7. And then, so this guy carries out 0, and the next guy is going to carry in on 0. So I'm going to make this carries 0. Okay, so the first adder has an output, it outputs the carry 0. Then the next adder has its input, its carried input is carry 0. You guys see that? Okay, so so let me do the outputs first. So that's 0, 1, already did the outputs, I just need the inputs now. Yeah, carries 0. This will be carries 1. This will be carries 2. I'm sure I screwed something up here, but we'll know when I compile it. Carries 3. Carries 4. Carries 5, and carries 6. All right, cool. So that should be a full adder chain. Ripple.
There's one thing. If you go up, the parentheses should be a bracket, and the full adder at 2.
Oh, at 2, okay. Yeah, I see it. Oh, thank you. Yep. So I need a bracket there. Yeah, there we go. Okay. So, all right, so that is saved. All right, now I'm going to try to vlog it. So vlog add8.sv. And, oh, wow. No errors. Cool. Okay. So then over in ModelSim, then to test it, I just have to switch what I'm simulating. So I'm going to go over here to the Library tab and, how do you refresh, I guess? Yeah, there we go. I had to right-click and say refresh. And when I did that, add8 appeared under my work library here. So now I can just right-click it and say simulate. Yeah, simulate. And so that'll close my current simulation. It'll open up a new simulation where the top-level design is add8. Of course, it will still include 8 full adders, but those will be in the hierarchy now. So yeah, if you look at add8, I drilled down in add8, and I've got 8 adders that are in the hierarchy, and then add8, I can then just I can force. Actually, I'll just type it in. Force A to be 8'D20, decimal 20. Force B to be decimal 30. And when I run that, hopefully sum is 50. Go back over. Oh, I forgot to add forgot to add them in my wave. Okay, so I'm going to right-click these guys, say add to wave, and then I'm going to run it. And the problem here is that because I'm going to hit the zoom full. Because I added them to the wave after I had already simulated 100 nanoseconds. I don't have the data prior to that, but that's okay because I didn't change it. And so now I've got hex values. So if I right-click here and I say radix decimal, okay, you can see there you go. And I'm adding 20 plus 30, getting 50, and the carries are 28, whatever that means. Okay, makes sense? Okay, so now I've simulated it. Now I want to put on the FPGA. So how do I do that? So for that, I need to, now you guys might have already noticed this from the project description, but I'm going to have to create another module that will serve as the top level module for the FPGA. And I need that because all of its inputs and outputs have to have special names that are coded to the pins on the FPGA. So for example, if I want to use the switches as input and I want to use the LEDs as output, I need to refer to those by their special names, right? So to set all that up, I'm going to go over here to Quartus. I just have to start Quartus. Now this is the part, by the way, we've provided a script for you guys. You won't necessarily have to go through Quartus, but I like to just show it to you so you know what's going on behind with the script. So the first thing I'm going to do is create a new project. And so file new project, and then I'll call it, yeah, it's fine, adder. What's the name of the project? Adder, directory is adder, it's fine. Empty project, no, actually, I'll add the files later. Okay, so here's the tricky part here. You have to select which FPGA. We're using the Cyclone 4E, I believe. Yeah. And its package is a FPGA, that stands for flip chip ball grid array. Pin count is, I believe, 780. And the speed grade is 7. And I think of those, we're looking for one that has 115 in the name, of which there are only 2. And I think it's this one here. Yeah, it's EP4CE115F29C7. That's the part number. Now, you guys won't have to do this if you use our script, or actually if you use we give you a file a QSF file. That's the name of the project file for Quartus. That's what I'm creating here, but we're going to give it to you, and that information will already be in there. Okay, and then finally, once I have that, I have to also load in a pin mapping file. Hopefully I have, do I have one of those? Let me make sure. Do I have one? QSF, right? QSF is the project. I believe that's also, yeah, there it is. Pin assignments. I do have one. Yep, I got one in my home directory here. Okay, so the other thing I'm going to do, and again, you guys won't have to do this, is because it's going to be already in your project file that we gave you in the skeleton, but I just want to show you how to do this from scratch. If you go over here to assignments and say import assignments, I need to import my pin assignments. So these are where the names come from. So ultimately the FPGA has a two-dimensional grid of pins on the bottom. Each of those pins have to be associated with like an English name that you use for the input and output. So if I go over here, now that I've imported that, if I go to pin planner over here, you can see, it's kind of hard to see at this resolution, but that's the underside of the FPGA, and down here is a little like Excel spreadsheet of all my pin names I can use, right? So in my case, what I want to use is LED R and SW, which are the switches, right? Now, one way you would know that, by the way, is if you actually look at the FPGA board, the silkscreen layer on the board has these names. A lot of the components have the name in silkscreen that directly refer to what you'd call it in your design. Not for the more complex chips, but for the simple stuff, it's in there. So I've got my pin planner and I've got the right FPGA, so all I got to do now is go back to Quartus and create a top level design. So I'll just say File, New, SystemVerilog, HDL, Verilog HDL, yeah. And I'm going to call this module top, and I'm going to have input logic. Notice I'm using the text editor built into Quartus, which is kind of crappy. So I'm going to have input 17 down to 0, SW, those are the switches, and output logic, how many LEDs? Oh, 17 down to 0 LED Rs. Okay, LED red, okay, and then, yep, that's it, end module, ends module. And then all I'm going to do here is I'm going to create an add8 and call it my adder, and I'm just going to connect this guy to I'm going to connect it to switch 15 down to 0, 15 down to 8 rather, because these are 8 bits, right? I need two 8-bit inputs. So I'm going to take bits 15 down to 8 of the switches and give that to A, and then B is going to have switches 7 down to 0, and then again I used the wrong kind of parenthesis there, okay, and then what I call it, sum is going to go to my LED R 7 down to 0. All right, I'm done. So now I can control the adder directly by flipping the switches and seeing the output on the LEDs, if this works. Okay, so to figure out if this works, I'm just going to, I need to bring in, I need to save this first, top.sv. Why is it, adder. There we go, top.sv. And so now I have this. If I go over here to my Files tab, it shows that's in there. Now the question is it going to find those other modules? Do I have to add them, or is it going to find them by itself? I wonder if it'll find them. So presumably the full adder and the add8 are not in my project, but they're in the same directory as my project. So I think Quartus is smart enough to find them in there, although I should have added them to the project, but I think it'll find them. As long as they're in the same directory, it'll find them. It'll look for, that's of course the reason why you want to name the Verilog files the same as the module. That's how it finds them. It just looks for names of files that match the names that you're instancing in your code. Okay, now here's the part that causes students to throw keyboards. This can take, didn't find them, I guess. Oh, I actually had an error, okay. Something about a comma? Oh yeah, I forgot a parenthesis here. Yeah. And then did I have too many here? I bet I had too many at the end. Yeah, okay. All right, come on. Okay, now this is going to take a while because, it takes a few minutes because it's compiling the code and converting it to a netlist, and then it has to map it onto the primitive modules that are available on the FPGA, and then it has to place those onto the FPGA and wire them together. And then it has to generate a bit stream file, which is how you program the FPGA. In Quartus, it's called a SOF file. SOF, it stands for Serial Output File, SOF, S-O-F. That's the physical file that gets sent directly to the FPGA and causes this circuit to snap into existence. Yeah, my adder is undefined, of course. All right, I'll add it. Assignments, settings, files. I probably have the, yeah, it's right here, buddy. Come on. Add 8, full adder. Those are the two I want to add, right? Okay. I thought I could find them, but I guess I was wrong. All right, oh, come on, buddy. Did it add them? No. My resolution is not allowing me to. Okay, let's do it this way then. Let's go to settings, files. Can I make this smaller? Ah, that'll work. No, I can't do that? Oh, that's awesome, Linux. Oh, that's awesome, yeah, okay. All right, so I can add these guys and hit open. And then I'm gonna have to scale my resolution up just to hit the OK button. Or scale it down, I should say. Let's go down to 150%. And then let's go to scaled mode. No. Oh, there we go. Now we're good. Okay, okay, and we're good. All right, let's go. Come on, buddy. Compile for me. Now, one of the things you're going to notice when you run this is, oh, by the way, what I'm doing now is a step that you get when you use our script, CSCE 611.sh, and run compile. It'll do this in the command line. And I'm not sure, I don't remember if it gives you all the messages when it's compiling. I think it does. But one of the things you'll notice is that there's a lot of messages that it prints. There's a lot of info, and in some cases you'll get warnings. Some of the most of the warnings, if not all, you can't do anything about. They relate to stuff that you have no control over. But it's very verbose. My adder, oh, adder undefined. Oh, adder, because it's not adder, it's add 8. Did I not put add 8 there? I did put add 8. What's it talking about? Design entry, adder is undefined. What am I missing here? My add 8, my adder, there's add 8. It's called add 8. I got top. Oh, I know why. I didn't set my top. Oh, yeah, sorry. Forgot a step. Right mouse click this and say set as top level entity. So my project name was adder, and it assumed that the top level module would be called adder as well. But I have a mismatch. I have a project called adder, but my top level is top. So I have to go and say set as top level entity and rerun it. Yeah, that was, I just did a right mouse click on the file, adder.v, and said set as top. It has to know where the design root is, right? And so it didn't know that, so that's why I got that error message. Okay, so anyway, I was saying that there's a lot of warnings sometimes you'll get. I'll probably get a lot of warnings here because I don't actually specify a clock anywhere because I'm using combinational logic only. Most of these tools are expecting you to have a clock signal. It's expecting you to have sequential logic in there because almost every FPGA is going to have sequential logic. This one is purely combinational, much like the one that you're doing for Lab 2, and so there's no clock signal yet. We'll eventually get to where we're having that. The other problem, for example, is like LED-R. I'm only driving 8 of those, right? But there's 18. What about the other 10? Well, they're going to be floating. So there's going to be some warnings in there where it gripes about that. And I'm sure there'll be some other things that it's going to complain about, but it should. Now, you might say, what are you going to do? What can you do about it? I could have set them to 0. I could have just hardwired those guys, the LEDs I wasn't using to 0, but I was too lazy to do that. So they're just floating. So I've got 10 LEDs that are going to be floating, which means on the board they'll be dimly lit. And then the other 8s will be my sum, adding A and B together. So found invalid fitter assignments. That's weird. I don't know what that's all about. Number of processors has not been specified, which, hey, come on, you can figure out how many processors you have if you're running on a come on. What's wrong with you? No clocks defined in design. Well, there you go. I was predicted that one. Number of processors has not been yeah, how many times are you going to say that? Generated file, yeah, okay. All right, is it done? It's done. Cool. All right, now that it's done, I can double click on program device. And the hardware, you'll notice this is the programmer. And again, this is what happens at the command line if you just say CSCE 611.sh program. But this is what it looks like in the Quartus GUI. The hardware should say USB blaster. Oh, by the way, I want to mention that too. The USB blaster is when you plug the USB cable into the leftmost connector. You got to make sure that you have in the right one, because the other one is for the host. Is it host or on the go? Or no, actually the second one's device. So if you wanted to program the FPGA to act like a USB device, then you'd use that middle one. And if you wanted to program the FPGA to be a USB master, or what they call a host, where it actually controls a USB device, like a thumbstick or thumb drive or something, then you'd use the one on the right. But the USB blaster is the one you use for program and debug. And so that's the one. Make sure you get on the right one. Okay, let's go. Let's hit start. Okay, now you'll see that it stopped blinking and it's programming. And yeah, so hopefully, yeah, so you can see that I've got a couple. I'm going to put all my switches down. Okay, so all the switches are down, no LEDs. And I was wrong. The floating LEDs don't come on dim. They're just out. But if I set, add 1 and 0, I get 1. If I add 1 and, let's add 1 and 3, I get 4 in binary there. If I add 3 and, uh-oh, I just reset it. I pulled the power cable out and I reset it. Yeah, these are, as I mentioned, these FPGAs are volatile. They have volatile memory. So if you take the power out, it'll reset the configuration. But that's okay, because I can just reprogram. Oh, no, it's gonna make me jump through hoops. Oh, no, come on, you do it. Program. Now, last semester, by the way, we had some issues with programming these boards in the lab. I spent all semester trying to figure it out. It was very unreliable. Some of the machines would be fine. Other ones, you'd have to kind of unplug and plug back in. But Rasha, who is teaching 313 this semester, she thinks she's figured it out. She thinks the reason that was happening was because we had only the 64-bit version of the libudev library installed on Ubuntu, and she had to install the 32-bit libudev, which is the module that controls, connecting devices like this in the USB, generic USB devices that don't have a driver. So she thinks she's figured it out. So hopefully this will be reliable. But in this case, it's not working because I turned it off while I had the programmer open, and so I'm going to have to restart. I have to restart Quartus to get it to recognize it again. But that was essentially it. Any questions about that? I know I went through that fast. Yes?
Does your script actually run like Quartus in like a headless mode?
Yes, yeah, it's headless. Okay. So Quartus and ModelSim both use Tickle, the TCL tool command language. And so yeah, there is a headless mode, and you can script both of them. It's a pretty powerful scripting interface. In fact, Charles has found things that you can only do through Tickle that are not available through the GUI at all, some hidden features that he found. So he got pretty good at doing that. I like to use the GUI myself, but I don't know. I never had to script anything too complicated with this stuff. By the way, if you want to go into the headless mode, I think it's Quartus underscore, you can see it, it's like Quartus underscore STP, I think it is the command that'll, all right, let's try it. So terminal Quartus underscore STP, ASM, something. Oh yeah, STP, there it is. Yeah, I got a library error, but yeah, I think that'll work. Okay, so let's go ahead and see what else I have here in the slides. So I covered I covered simulation. So this slide just tells you how to get vSim started. This shows you a couple of the windows. Now you don't. Now one of the things that you notice that I use the vlog command to compile the files. You can use the vlog command in a bash terminal, or you can use it in the command line in Quartus, or you can do it through the GUI. If you go to compile on the pull down menu and go to compile, you can select files to compile there as well. So there's multiple ways to do that. And then simulate is just under simulate, start simulation. And those are the windows, and I showed all that. And yeah. And then I mentioned too that in the command window you can type things like force A. In this case, I'm using the VHDL hexadecimal designator, but you can use either one in ModelSim. So I'm just saying force A to be dead beef and hex. Or you can say force op. Again, I'm using VHDL style here where I've quotes to specify a multi-bit value, but you guys can use the Verilog way to do it, which would be, in this case, would be 4'B0001, right? And then or you could just have a single bit value. Run is just run with the amount of time you want to run. And then this is the command that I use through the GUI to initiate the clock, to cause it to toggle at regular intervals. Now, when you do that through the GUI, it will show you the command in the command line window. So if you want to put in the command yourself, you can do that. You guys follow me? So in other words, what I'm saying is that everything you can do in ModelSim, you can do either through the GUI or through the command line window. Okay, here's a script. You can also save a set of commands as a .do file, which is just a script. Then you can just say do space in the name of the file, and it'll go through this script. This is how we used to test everything in this class until I started focusing more on test benches. So a do file in ModelSim would allow you to actually to set the stimulus, right? To set inputs to your design that you want to test. The problem is I never figured out how to have this kind of file read the outputs. I think it can be done. I'm sure it can be done. I just don't know enough Tickle to do that. So as a result, we use test benches instead. Test benches allow you to set the stimulus and also read the outputs and compare to what you expect them to be. And if there's an error, it would print the error message, right? That's called a self-checking test bench, right? If you write a script like this, you have to pretty much look at the wave and figure out if it's working just from the way the waveform looks, right? Which kind of sucks. And it's not very reliable. Okay, this just shows the Quartus. Now I mentioned, there was that chip name, EP4CE 115 F2 C7, F29 C7, in case you're interested in setting that up. And there's the pin assignments file, which I showed both of those. Again, we give you a QSF file where that's already set up for you, so you don't have to worry about it. Okay, and that's all we have until we get to the always statement, which I think I'm going to save that for next lecture, because that's going to take some time to get through that. But once we get through the always statement and the test benches, we'll have pretty much finished out all the parts of Verilog that I plan to cover. Okay? Okay. Thank you.